yeah, I work at Deliveroo as a data scientist. And I want to give a talk that's a bit more, I guess it's slightly more technical, but don't worry, there's no maths in there. There's no maths in here, so don't fall asleep. But yeah, so we talk about A/B testing, we talk about experimentation, and often we're like, oh, we need to reach a sample size, get significance, and yeah, let's roll this out. But at least from what I've learned being a data scientist in a company, or I hope I'm like quantitatively literate, is that a lot of people say a lot of these terms without necessarily knowing what's behind them. And so as an analyst, when you want to run an A/B test or an experiment, there's two main questions you get. And it's basically, should I roll this out? And how long will it take before I know? And so I want to basically, with this talk, address the latter of those. So how, as an analyst, we work out how long an experiment needs to take before we can decide whether to roll it out or not. So that's the idea behind this talk. So I'll first start off with sort of like motivating what's called power analysis. So it's this power analysis that you might hear analysts say they go and do this weird and wonderful thing and then come back with a date as to when this experiment we finished. So I'll motivate that, and then I'll give some sort of visual intuition. So rather than go through with maths, so any technical people that are getting their pens and paper out, don't worry, there's no maths in here. And then I'll go through at a very high level an example of how we might actually go through and do that. So that's the plan. That's the plan. So yeah, it's not mathematically rigorous. So motivation for the need for power analysis. So we've had a few suggestions already about what features we can actually release. So we're a company, we come up with this new idea for a product. It might be a new color button. It could be which version of an advert is better. I'm an algorithms data scientist, so I usually try to develop machine learning models. So if we develop a new algorithm, is it better than what we currently have? Is it better than what people are actually doing? And that will get A/B tested as well. So at Deliveroo, we A/B test quite a lot. There's always an experiment, probably multiple experiments running. I have one of our colleagues over here who works in product analytics, Alon. So yeah, and he does a lot of that stuff, so he can actually tell me if I'm going wrong as well. But yeah, so basically we define a feature, and we want to know, so we need to test it alongside what's currently used. But the big question is, how many is enough? So often when we talk about releasing like a new color of a button, we want to allow people, it's people that use it, and so how many people do I need to see before it's actually enough? That's the big question. So let's motivate this with a coin toss example, and let's see exactly why testing on too few people doesn't give us what we need, right? So with this coin toss, I have a coin, and there's two hypotheses. One is that it's a fair coin, it's 50-50. I toss it and it's even as to whether I'll get a head or a tails. The other is that it's slightly biased towards heads. And this is analogous to releasing a feature, right? Hypothesis one is usually that the feature is not better than what we currently have, and the second one is that it is, typically, right? So let's say I toss that coin 4 times, and I get 3 heads and 1 tail. And the question is, based off that, can you decide if the coin's biased or not, right? And what you should think about is, even if I have a fair coin, if I toss it 4 times, it's quite likely that I'll see heads 3 times. It can happen, right? The same as if it's 60% biased towards heads. It's likely that I get 3 heads, and maybe once I'll get a tails. So the idea is that if I only take a few samples, I can't actually tell the difference. And this is what happens if typically a product manager will come like halfway through an experiment or a day or two and just be like, how's it doing? Is it good? Has it finished yet? And I mean, you have a result. It might say that it's better, but I don't have enough samples to tell you definitively if that's actually true, right? So if I now toss that coin 1,000,000 times, and now I get over 600,000 heads and less than 400,000 tails, I have a bit more information. I'm probably a bit more confident that that coin is biased, right? So we have this idea that the number of samples that we see gives me a better idea of the confidence of my conclusion, right? And this is, so yeah, we can get that. So this is the idea of statistical power. So very loosely, you can think of statistical power is just a probability. That's all it is. So we use this term power, right? It's just a probability. And it's a probability that I will correctly conclude that we should roll out the feature, that it's better, right? That's what we mean by statistical power. So the idea is when we do this power analysis is we want to get an idea of the probability that I'm going to correctly conclude that this feature is better, right? That's the idea of power analysis. That's all it is. And that's what your analysts will have to do. Or if you end up buying like this off-the-shelf solution like Google Optimize, they'll have this sort of stuff behind the scenes and they'll just come back to you and tell you, this is the number of samples that you should use. But this is what goes on behind the scenes. So, as we can imagine, what happens with more samples, remember with the coin toss example, more samples meant we are more confident, right? We get a higher power, right? And it's important because typically we're very conservative about rolling out a new feature. So you heard earlier that we might have this 95% confidence, right? This is relating to the current feature. We want to be sure that if we see a value and it's bigger than what we currently have, it better be a lot bigger, right? We're going to be even more conservative about whether we're going to release that new feature. All right, so now we get on to pictures, pretty pictures. I like pictures. It's good. Okay, so let's do this. We've assumed that, let's say we got this website and we have this conversion rate, and we typically call the status quo, or what we currently do, the control, right? And we're going to just put this at 0.2 or 20%. That's currently what we see, right? This is that value. The thing is, over different days, it might not be exactly 20% of people that convert, right? It might be 19% or 21%. So there's a bit of variation about this, and that's what this bell curve type thing is saying. There's a bit of variation in the actual, say, daily conversion rate, let's assume. But if I know, so I take this over, I could say like 6 months, I could say a year, that variation, right? I can build up how much it varies, right? I can build up how much it varies. And then I end up with if, right? So if I know that my conversion rate is 20%, one day I release a feature and all of a sudden my conversion rate is 80%, you're going to say, wow, that feature did something. So there's some threshold, there's some cutoff, right? At which if I see a conversion rate higher than that, then it's likely that my feature did something, right? And that's what this pink bar is all about, right? So we pick this what we call a critical value. So here it's 0.28. So this dashed line is this true conversion rate, this true 20% rate. And this is what we don't know. This is the important thing. We never know the true value, because if we did, we wouldn't need to run an experiment, right? I hope that's kind of evident. So we never see this dashed line. That's an important point to make. We only see this bell curve, right? This blue area, notice that there's some of the blue line on the right-hand side of this pink line. That tells me that there is some variation that goes further than the critical value, but it's so unlikely that if I saw it, I'm just going to conclude that the feature's better. Right? And this is what we call a type 1 error. This is the error. So we typically set that at 5%. So when we talk about a 95% confidence, right, interval, 90, this is what we're talking about. We're actually allowing a bit of room for error, right? So, right, yeah, we don't know that value. Now, we release a feature. We release a feature, right? And we run an A/B test. So this is my new feature. This is my control, all right? This is the feature and the control. Again, I don't know the value of the dashed line, right? Otherwise, it'd be pointless doing this. Right? I don't know the value. But what we care about is all of this. Anything to the right of that pink line tells me that I should roll out that experiment, that feature. And so as an analyst, what we want to do is calculate how much underneath that new feature is to the right of that pink line. And that's your power, right? This is what statistical power is. It's just the area that's to the right of some pink line, right? That's what we do. as analysts, right? So that tells us, and we usually set that at about 80%, right? Typically we set it at 80%, but it can be whatever. However confident you want to be in that conclusion, right? So if you want to be 95% confident in that conclusion, you'll take more samples. You need that. So what happens if we take more samples? What's actually happening? So in this visualization, the variance gets thinner. So the more samples I take, right, I'm more confident about what this true value is, right? So if I toss the coin 200 million, trillion, zillion times, I'm more likely to see 50-50 heads or tails, right? And I'm more likely to conclude it's 50-50. So that's what's happened, right? We zoom in on that true value. But in the case, so this is more similar to the case where you toss the coin 1 million times. If we don't take enough samples, then I'm very unsure, and then it overlaps quite a lot. And the problem we see, this is what happens if you don't have enough people on your site and you can't finish a test, is that even though my true value, which is in the middle here, is better than the true value of the control, because I've set my critical value over here, this pink line, there are plausible values I can see for conversion in my new feature that I would still just be like, nah, I'm not going to release that, mate. Nah, it's not good. So this is similar to the case if we don't have enough samples. And so this is what we do as analysts. This is what we have to do. Right? So where we talk about, let's just release a new feature and run it for a bit and see if it's better, we have to go back, sit down and play with these sorts of things and try and work out an area under a curve. It's great stuff. I love my job. Also, there's a chance that we won't roll out a feature, so I covered that. So a little example. This is just how we might do it. So when we actually go away and do this analysis, we don't actually look at these graphs. It's like what I've shown you is what we're trying to understand. So we can understand it in terms of these graphs, but we don't usually plot those graphs to figure out how it's happening. So sometimes we don't plot those graphs because I've put on like an ideal shape there, but sometimes depending on the type of data you have, the type of experiment you're running, where you're doing it, it might not, the shape of the graph might not look like that. And also some of those, so those bell curves, we call those distributions, some of those aren't actually tractable. If I write down maths equations, I can't actually write down an equation that will tell me what the curve will look like. So in those situations, we do something else. So we do something called a Monte Carlo power analysis. It basically means simulate the stuff with random numbers. This is what happens. So it's fancy words. We use these fancy words. So what we'll do is we'll take historical data. So this is what we have to do. We go back. Someone says, we want to release a new feature on this button. They're like, okay, we'll work out how long we need to run this experiment for. So we'll go back. We'll go to the data warehouse, wherever you store your data, and we'll take data for, I don't know, like a few months or a year, whatever we need. And we might see person one came to the site and they clicked the button, or they bought something, so they converted. So that's a one. Person two came, they didn't, right? And so we'll build that up. Typically we'll have millions of people here, or hundreds of thousands, right? Not just 6. But here we'll have 6. So in this case, 2 people converted out of 6. So our baseline conversion rate is 0.33. So what we estimate, that true blue dashed line that we saw is that would be our estimate for that. But we don't know, right? We don't know in reality. And then what we do is, when I say we simulate, we try and pretend we run this experiment with old data. That's what we do. So what we do is we take all of those people and we randomly give them a couple of groups. We randomly allocate them to group A, randomly allocate to group B. All right, so we just say that we'll do that. And then this stuff, don't worry about, we multiply some stuff. So we basically pretend we know. And this is where it's important, where you estimate the effect of your feature. So you have to say, I think my feature is going to have, say, a 3% uplift. And if it is that, then how many samples do I need to work out how long I need to run? So that's one of the things that, as a product person, you guys can do to help us analysts, so that we don't have to estimate those things. If you got an estimate for us, that helps a lot, I promise you. So here I'm just going to pretend that we've got a 3% relative increase. So I'll say, okay, this feature's got a 3% relative increase. And then I'll just simulate some random numbers. Did they convert according to this effect that we have? I'll simulate according to that effect. And so I'll generate random numbers. So now I can have a conversion rate for group B and a conversion rate for group A. Right? So just because I've simulated, just done that, and then I can just test. I can just do, would I have observed a difference? Would I have observed and said, we can roll out that feature with group A and group B? That gives me 1 point. Typically, we do this thousands and thousands of times. So we'll reallocate A and B on those same people and then run the test again. And then we reallocate A and B, run that test again. And so what we can do is then we build up this curve and we do it with different numbers of samples, right? Different numbers of samples. And this y-axis here, this is the area under that, this is our estimated area under that gold curve that we saw earlier, the power, the statistical power that we're going with. And if we set a confidence at which we want to correctly conclude that the feature is actually good, all right? We see where that curve reaches there, and we say, great, about 13,000 people. So if I get 1,300 people to my site in a day, this experiment needs to run for 10 days, and then we'll get there. So it's completely an estimate. It is an estimate because we're trying to estimate the effect size, and we're also using historical data to actually say how many people would come to our site, so how long will it take to get there. And that is how we end up providing you with an estimate of how long an experiment will take. And so yeah, we can do that with off-the-shelf software tools, and it tries to do this for you and comes up with estimates and everything. If you want to learn more about this, it just so happens that a few of my colleagues wrote a blog post about this. So Dan, my boss, and a couple of analysts, data scientists at Deliveroo, wrote an entire post on how we do Monte Carlo power analysis at Deliveroo, and they do different types of problems and things like that with code. If you're a technical person, it has the code there to actually perform that and do it. So yeah, you can have all the slides to this, by the way. So the link's in the slides. I'm happy for Bav to go share. Oh, sorry, the new organisers to share it out. That's fine. So yeah, that's pretty much it. So we covered basically how we work out, as an analyst, from my point of view, how we work out how long an experiment needs to take, right? So why we motivated the need for large sample sizes. It allows us to be more confident about our conclusions, right? We define this statistical power. So often you'll hear analysts go away and do power analysis. It is about trying to find the area under that gold curve. That is literally what we're trying to do. And we saw that visual definition, and basically at a very, very high level, and you're not going to be able to repeat what, power analysis just for what I showed you, but we covered what we actually do. So it's basically take historical data, simulate the experiment as if your historical data was going to be what your new stuff is. So, and yeah, I hope you kind of learned something from that. I hope that was good. So yeah, thanks for listening.